Hello and welcome to yet another of my ÄKTA chromatography teardown videos. This is it's part of my day job, so it's fun to document this stuff, and I hope that it is helpful for some of you to understand a little bit more about how these systems are put together. This is for those of you who have not watched the channel at all, this is a chromatography system, which means it's a laboratory instrument for separating closely related species of molecules, and you should look up more about that or ask questions if you'd like to know more. This system that we're talking about today is the formerly GE Healthcare, GE Biosciences ÄKTA line. It used to be part of Amersham Pharmacia, but they divested the line, and now it is like all these kind of businesses, they move around a bunch. So they get bought and sold and everything else, and some sort of strategic initiative happens and they decide to move it somewhere else, and the stock price goes up or down and all that kind of stuff. So these guys, these poor schleps that are in Uppsala, Sweden, working for the ÄKTA organization, are now under the umbrella of Danaher, which is another mega monster corporation conglomerate that has industrial stuff and science stuff and I don't know what else, but doesn't matter. Not part of this conversation. This is part of one of the slightly earlier generation. I think it might still be active. The idea is still active. This is the controller for the ÄKTA chromatography system, and this is the control unit 950 or CU950. And looky, I've already done the job of tearing out the innards. So you can see there were some LEDs on the front, power, PC, and the ever ambiguous system light. So we can get an idea of what power does. This probably means connected to the PC, and system means the system. I don't know what it means. So 4 screws and we were into the meat of her. 4 screws in the corners and we were into it. Let's take a look at the back panel, and then we'll go through how this connects up. So obviously input, the unstated power input, 12 to 24 volts at 1 amp. This is DC. It's a 3-pin mini DIN connector. There's also a USB type B. So this is the old school, can go up to the USB 2.0. Speed there. This is clearly Ethernet with its link and activity lights. And then this Uninet -1, we don't know what that is, and test, we don't know what that is also. We see from the tag here some sort of probably part number. The serial number 8670, not exactly a long serial number, so this is certainly not something they make billions of a year. This has got to be the default IP address. They haven't put the zeros in, but they left the space for it, which is kind of interesting. Well, whoever designed this label, the IP address 192.168.98.34. So we're on a local subnet here, one of the reserved subnets, 192.168. You're probably all familiar with that. We have a waste reduction, WEEE here. We have some marks showing that this is been certified to a nationally recognized testing laboratory, and it is CE marked. And we're supposed to be warned about something, and we're not sure what it is because there's no depiction, but you should just be careful, I think is what this says. Just generally be careful. Take care. So GE Healthcare no longer. Biosciences AB, that's the Swedish idea of a company of some sort. You'll correct me in the comments because I do not know what I'm talking about there. And it is made in Sweden, yeah. Okay. So let's take a look before we go into the meat of that. Let's look at how that compares to the architecture of the system. And the system is a number of these modules that get hooked together, a valve, and this goes on and on. So there can be many of these devices, but each of these rectangles down here are a device. So we've got some kind of valve to control the flow of fluid through a system. We've got a pump here which pumps drive the flow of fluid through some kind of system. And this says UV, and that measures properties about the fluid in the system. So there's a fluidic schematic, which I have not drawn here, that would show how the fluid routes through this whole system. And then there's also a device schematic showing each of the devices that do that work. And all of those devices work in concert like an orchestra, and they need to be coordinated by something. So that happens to be our fancy little CU950 right here. So we have an Ethernet connection. We looked at that earlier. We have an Ethernet in USB, so actually we could have either of those going up to our PC. And I had a lot of fun drawing my DOS-like PC with floppy drives and look at that beautiful keyboard. That's a thing of beauty for sure. Because most of this technology is really quite old, so I stayed with the DOS-looky thing, because even though the newest versions of this ÄKTA software are skinned up to look pretty cool, they still are based on really old technology. Not to say it's bad technology or poorly designed. I mean, I think their architecture is really fantastic, but I think it could be updated now. So one thing about this that I can write in here is that this is the way that the CU950 talks to all the other devices is over something called CAN bus. And CAN, or you're probably familiar with LAN being local area network, which is more of this. CAN bus was developed in the 80s by the Bosch Corporation to be the controller area network. And who knows and who cares, but that was meant for cars. So the idea, and all modern cars really use CAN bus in them, all modern cars, when you press the window down button, that sends a message to the window motor to go down. It doesn't actually control a switch to click and turn on the motor. It sends a message over to the motor. So there is a network, and actually many networks inside your car, and probably most all of them are CAN bus. There are some that'll be Ethernet now in certain cars, but many of them will be CAN bus also. And CAN bus is interesting because the device can talk on the network and anybody else can listen at the same time. The controller doesn't necessarily have to be involved. This pump can send a message and the UV can receive the message and do something autonomously without even involving the controller. The controller, it's a bus, which means whatever goes on the bus, everybody gets. But the controller can see that it's happening, but the controller can't necessarily intervene. That's reflexive. Something happens here. This UV is watching for it. The UV makes a change based on something that happened over the pump. The controller doesn't even need to be involved in there. There's a lot of other interesting things that happen in the CAN bus, like a sync, because you might say, what if two things need to happen at a very exact time? So there's some neat things that go on in CAN bus with sync. So it's certainly is a mature technology. And I'm quite sure that's what Uninet 1 is. Uninet 1 is a CAN network. They've just rebranded it as CAN, so Uninet 1. And why the 1? Well, they've got a Uninet 2 also. And you can imagine CAN bus has evolved, so they probably have some devices that some engineers said, what if we took advantage of the advantages of some newer iterations of the CAN bus specification and the chips and things that come with it, and we could use CAN bus 2, or it's not called CAN bus 2, we would call it Uninet 2. This is like CAN bus FD, and there's some things called CAN open that layer on top of this for industrial control. So we're not exactly sure, not at this point, what they've got going on there, but maybe we'll take a look and see if we can figure out some of that in a later video. This video is just going to take a look at the Uninet, not the Uninet, come on, at the CU950 controller. So I've already disassembled this, and we'll just take a preliminary look at what parts are on here and see if there's something we can figure out. So I've looked up a number of these data sheets already and had a pretty good idea of what's going on, but the first thing you can see is that we've got an old school compact flash card inserted in here, and there's nothing special about it. It's 128 megs, so it's certainly pretty old. This is 2023, so you wouldn't touch anything at 128 megabytes now. But it's nonetheless, it's in there, and it's in the compact flash interface, which is a parallel interface very close to the IDE or integrated drive electronics interface that you'd see on a 40-pin or 80-pin type hard drive before the SATA serial ATA specification hard drive came into play. So this will talk SATA ATA commands to the microcontroller to send and receive data. So there's this wide bus here. And you know, this chip, you don't see a wide set of bus pins coming out here. Now they could be hidden in the inner layers, but I suspect these guys are line drivers and probably bus multiplexers. And I did look up a little bit of this, and they are probably that. So there's no real need to run the full width of the IDE bus out here anymore. So we've got that. These guys, if you're kind of following along at home, these are flash chips. These ST, these are like slow to write but fast to read. So this will be where the OS for this thing is. And these guys here are going to be the RAM that go with it. And then we've got a couple other interesting parts over here. We've got, I've lost it now. There's a Bosch part on here, which I'm sure is the CAN driver, and I've lost that for the moment. Let's see if I can find that. This is clearly the USB controller, Ethernet controller, sorry. This is the Ethernet controller. And this is the magnetics. So Ethernet needs some magnetics, some coupling, some transformers to convert the line voltages. And what will be underneath this, newer chipsets, the magnetics are done differently electronically. But at this point, they were still little transformers. So here's one of these magnetic couplers. And you can see Ethernet has 4 pairs of wires, and you can see there are 4 transformers in here, 1 for each pair. And this converts the differential signaling into the single-ended signaling that we need to drive into this chip. So this is all clearly, you can see it comes right off the Ethernet connector. Comes right off here, goes to this chipset. There'll be a second set, a pair of outputs of this chipset that drive the 2 LEDs here and here. And in more modern implementations of Ethernet, the magnetics will be built right into the back of the jack. So that'll be called a mag jack right in the back of this Ethernet jack. I thought I had a Raspberry Pi sitting right here that I could show you that, but I'm not seeing it immediately, so I'll apologize for that. This is the CAN stuff going on here. So here you've got 2 CAN transceivers. You've got some optical coupling here. This is so that if you don't blow this board up if you send the wrong voltages, some good safety stuff going on. Some optical coupling, and then you've got the CAN transceivers here, and I think, is that the Bosch chip there? Maybe it is. So there's a, this was built probably around 1999, I think, and there are some chips here that are single chip solutions to get your CAN right into the microcontroller. And then, of course, here we have the big kahuna, the brains of the whole operation. This is the microcontroller. So this guy is the main CPU, an XPC 823. This was from Freescale, which is no longer. But this actually has 2 processors in it. It has a RISC, it has a PowerPC core, and then it also has a 32-bit micro subprocessor. So it's allowed to do some other stuff at the same time, like offload onto a coprocessor for more real-time activities. I do know, because I've already hooked up to the RS-232-1 and 2 and the BDM, which I have to assume is some sort of debug. I don't know why it's BDM. If anybody knows why it's BDM, that would be great. But RS-232-1 and 2, we can definitely get some, we can watch some boot stuff happen, and we can interact with this OS while it's running. It's running VxWorks. So VxWorks is an embedded real-time operating system. I think a lot of people now use FreeRTOS more than VxWorks. Maybe for some mission-critical applications, VxWorks is still the way to go, but probably not in this one. So, and then back here, we've got this vertical thingy with 3 resistors next to it. That would be the LED tower. That would be the power, PC, and system lights that we looked at the beginning. Around the edge, we can see they're proud of their name. They didn't really think they'd change names, apparently, because they stayed with the GE Healthcare. The CU950 is the model. This is going to be something about the board part number. Some fiducials for assembling the board. Power in here. oh, there's a reset or some kind of a switch here that's unlabeled. So we saw this hole above the 20 sticker, and that's going to go into this switch here, which we can press with one of our little DuPont wires. Clicky, clicky, clicky. And not exactly sure what they're doing with this current shunt here. That is yeah, there's some power protection stuff going on here. If this is a GE healthcare product, I can guarantee you this board would have gone through review through GE corporate, because the last thing they would want to do is kill somebody, hurt somebody, have any kind of negative thing go back on them because some sort of power issue came through. So they will be 100% compliant without argument with their nationally recognized testing laboratory, or NRTL certification. They won't play with that at all. You can see all the shielding has been done quite well around here. I know that's not in focus. All the shielding and stuff has been done quite well. Everything is assembled really nicely. These little brackets have PEMs, or are they PEM branded? I can't. Nope, I don't see the 3 dots. You'd have to see some dots in there if they were PEM branded. So they've got these little fasteners in here, so it's not like it's sheet metal screws into a bracket that's kind of wonky. This is high price stuff, like super high price stuff. Look this up on eBay. The CU950, I think it still goes for $850. So yeah, this is like, and new this would have been, I don't know, $3,000-$4,000 probably for this module. Would be thousands of dollars. So they're going to do everything super well. So this power conditioning over here is done really well. I would imagine they're making 5 volts in here. I didn't look these up, but I imagine they're making 5 volts down here, and maybe 3.3 even at this age. We've got, I don't think I knew what that part was. I'd like to take a look at that part. Maybe a beeper. I don't know, to be honest. And I can't see from where I am, so that'll have to be a follow-up. Yeah, that's what I've got. Oh, and there's a sticker over here with presumably the serial number on it. Let's see if we've got the, yep, 8670. We've got 1992, serial 8670, the model CU950. That does look like their part numbering scheme, 289-18124. And here we have a 289-18126 AB. So this is probably the bare board part number without the parts on it. Somewhere in here there might be a part number for the board assembled with the parts, and then a third number when you assemble everything on it. So those 3 assemblies would, highly likely, those would have 3 different numbers on them. Okay, and then on the back side, there's pretty much nada. There is a little bit of me reverse engineering here to get make sure I get my leads on correctly. And we've got a little bit of vias over here to get some heat out of that processor and get the ground plane all bonded together. And we've got no matched traces, it does not look like. So we're not going fast enough. This CAN bus operates at kind of megahertz speed, kilohertz to megahertz speed. So we're not really going fast enough to worry about signal integrity there. So here we've got a multi-layer board. Here's the back layer. So this is layer 4, 289-18126 AB, and this is going to be layer 4. And over here we've got, what, layer 1? And then this is probably a 4-layer board. Almost certainly this will be a 4-layer board. Got a crystal here to operate that Ethernet subprocessor. We've got a crystal here, I assume, for each of the NXP. Those are, if you're interested, those are SJA1000T is what that is. SJA1000T. And there's another NXP part right up here in front of each one that I don't know what it is. And then, as I said, I haven't refound that Bosch part that's doing the CAN control. I think that's on a different board I was looking at. That's right. Doi! I'm looking at too many things. I would guess that's the crystal to drive this Freescale. It may be 2. It looks like 2 crystals right here. So it may have 2 crystals. So lots of 4-leaded parts hanging around this chip here. And yeah, that's kind of a tour. If this is your thing, then this will be interesting. If it's not, wait for the next video when we get some stuff up here and we'll see if we can get a little hacky with this. Thanks for watching, and hope it was useful. If you liked it, of course, thumbs up, because that helps me know what videos I should be making. And subscribe, certainly, because that's helpful too. Yeah, this is kind of like esoteric stuff, so if you like this stuff, please do promote the Nikki Does channel. Thanks for watching.